So this is part 3 of the tutorial about implementing a functional language in Scala. In this part we will implement the parser. The grammar of µDhall is a simplified version of the Dhall grammar. Now let's look at that. It is defined in a format called ABNF, which is a specific version of BNF with some extensions. And so you see it's quite a long grammar. It's not so big, but it's heavily commented. And I'm just going to show you the grammar of µDhall. This is going to be much smaller. So these are some helpful definitions for things like white space and end of line and digits and so on. So here we have a first interesting definition, which is a label. Label means identifier, really. So identifiers cannot be one of the reserved keywords, so that will have to be a negative lookup, which we will implement. And other than that, you see identifier can be some alphanumeric character. Well, actually, alpha must be the first, must be a letter or underscore. And then there are alphanumerical characters, but it also can be a minus, a slash, and underscore. So this is a specific feature of Dhall, that identifiers can contain dash and slash. And the reason is, well, one reason is that Dhall does not support operators like minus and divide. And so why not use those characters in identifiers? Another reason is that Dhall is intended for configuration management, and configuration files sometimes contain identifiers with dashes. And why not just support that as a part of identifier? So a Dhall identifier could look like this: label dash next dash character. That we will do the same in µDhall. So it will also support dash and slash as part of identifier. Then we define what is a non-reserved label, which is identifier, but not one of the reserved built-in identifiers. So some identifiers are built in, or these are the ones: natural fold, natural subtract, type, and kind. And these are the keywords: let, in, for all, the symbol for all. These are the keywords. So identifiers cannot be one of those, and identifiers can be these, but they have a built-in meaning. So in most cases, it's a good idea not to use identifiers that have the same name. So then there are special symbols for lambda. So this is the Unicode for the Greek letter lambda. This is the Unicode for arrow, but you can also use ASCII equivalents. And then there's a plus and times. So now you see what happens if we wanted to add some more operators, or some more built-in functions, or some more keywords. Then you would have to add them here, and pretty much nothing to change anymore. So identifier is a variable or a built-in, and then we define what expression is. Expression is a lambda, or a let expression, or a for all expression. So, or it is an annotated expression, type annotated, and then we say type annotated expression contains an operator expression, which is something with a plus, something with a plus contains something with times, something with times contains something with function application, and in this way the parser introduces the idea of precedence. A times expression has higher binding precedence than plus, and that has a higher times binds stronger than plus, so plus expression is defined first, and then the times expression, which binds stronger, and then the application expression, that means applying function to arguments, that binds even stronger. And so in this way we define a parser that automatically has the right precedence for operations. So a comment here is that this is a very simplistic way of defining a parser in this way. It will be difficult to add more operations with different precedence. So there are different parsing formalisms and libraries where you can specify directly the precedence of operations. But we're going to use a very simple approach. So we're just going to say the parser is just going to parse these expressions in the hierarchy like that. So then finally we get down to primitive expressions, which are numbers, identifiers, or parenthesized full expressions. So that is the entire grammar. We have identifiers, we have natural literals, keywords, and then these types of expressions, and that's it. So we're going to implement it using the fastparse library, which is pretty good for this kind of prototype work. And I just translate these definitions, but at the same time I specify how we're going to create our algebraic data type out of the parsed grammar rules. So for example, the built-in is a grammar rule that takes one of the built-in symbols and maps them into our built-in case class. So in this way we define parsing. At the same time we parse directly into an expression tree of our custom type. So with the fastparse library this is done like that. It's pretty easy. So for example, a natural literal we just map into integers. Variables we map into the variable structure, and identifier we add we say it's a variable or built-in, but it already is parsed correctly into the structure. So then for example, application expression is the primitive expression, and then there's a white space, and then there's another primitive expression. So both of the primitive expressions will return our parsed structure. So now we have to now the application could be any number of them, right? So there could be an application of many arguments. So then we have to put applied on each one of them. So that's why I use the fold in order to describe these nested applications. So this could be at the same time application of queried function to many arguments, and so on. So in this way we just translate the grammar into code pretty much literally, and then we just add sometimes these folds, or we add map in order to translate into a data structure that we need. So in this way we parse. So let's see, there's some function to add in debugging the parse, which shows the error if there's any error. And here's a test. So here's a program that uses all the features. It's parsed successful, And here's a program that has a parse error. So the error is here. It's expected to have an expression or something, but instead it's a closing parenthesis, which is unexpected. So in this way we have parsed. Now, to make it quicker to parse, I define an extension method on strings, which is .dhall, and then the result is going to be that I'm parsing the string, hoping that the parse is correct, and if not, there will be an exception, but it's good enough for our testing purposes. And yeah, so also I add extension method print on Dhall expressions. So then I can say things like this. So parse this and then print the result using the pretty printer that we defined previously. So then the tests pass, and this is how we parse the µDhall expressions. So this closes the third part of the tutorial. In the next part, we will be evaluating expressions.